A lot of people buy a 3000-watt inverter first and then get confused about one thing. How many solar panels do I really need for a 3000-watt inverter on a 12-volt system? And at the end, I will show you a smart trick that can reduce your total system cost. Let's start with a quick and easy method first. We will assume a 12-volt lithium battery system, because most beginners start with it. It is simple, easy to find parts for, and cheaper at the start. But keep this in mind. High power at low voltage means very high current, and that increases cost. A 3000-watt inverter, running at around 90% efficiency, on a 12.8-volt lithium system, will draw roughly 260 amps at full load. Most 12-volt, 100-amp-hour lithium batteries come with a 100-amp battery management system. That means one battery can safely supply 100 amps. So, to handle 260 amps, we need 3 batteries in parallel. That gives us 300 amps total, which is enough for a 3000-watt inverter. Now let's calculate stored energy. One battery, 12.8 volts times 100 amp-hours, equals 1,280 watt-hours. 3 batteries, 1,280 times 3 equals 3,840 watt-hours. This is your total battery storage. A common off-grid rule is recharge the battery fully in one average day. Let's use 3 sun hours as a safe winter average. 3,840 watt-hours divided by 3 sun hours equals 1,280 watts of solar panels. So realistically, you need about 1,300 watts of solar. If you are using 375-watt panels, that means 4 panels. Quick summary. 3000-watt inverter. 3 12-volt 100-amp-hour lithium batteries. 3,840 watt-hours of storage. Around 1,280 watts of solar panels. This works, but it is not the best way to design a system. Now let's do it the correct way. Here is the mistake most people make. They buy a 3000-watt inverter and assume they need 3,000 watts of solar. That is wrong. Solar size is based on daily energy usage, not inverter size. You can have a 3000-watt inverter and still use very little power. Or you can use a lot of power and need much more solar. Let's go through a realistic off-grid example. Daily energy use. Fridge, 800 watt-hours. Microwave, 140 watt-hours. Lights, 160 watt-hours. Television, 200 watt-hours. Laptop, 200 watt-hours. Total daily usage equals 1,500 watt-hours. For off-grid systems, we usually design for 3 days of backup. 1,500 times 3 equals 4,500 watt-hours of battery storage. Now, convert that to battery size at 12.8 volts. 4,500 divided by 12.8 is approximately equal to 350 amp-hours. A good setup would be 2 12-volt, 200 amp-hour lithium batteries. Each battery has a 200-amp battery management system, so together they can supply 400 amps, which is more than enough for a 3,000-watt inverter. Now, let's size the solar. 4,500 watt-hours divided by 3 sun hours equals 1,500 watts of solar panels. That could be 6 250-watt panels or 4 375-watt panels. This system is designed around what you actually use, not guesses. Now, let me show you how to make this system cheaper and easier. The problem with 12-volt systems is current. 1,500 watts divided by 12.8 volts equals about 120 amps. That means bigger charge controllers, thicker cables, more heat losses, higher cost. Now, look at higher voltage systems. At 24 volts, 1,500 watts, divided by 24 volts, is approximately equal to 49 amps. At 48 volts, 1,500 watts divided by 48 volts is approximately equal to 29 amps. Lower current means smaller and cheaper controllers, thinner wires, less voltage drop, easier installation. My recommendation: 48 volts for cabins and homes, 24 volts for vans and recreational vehicles, 12 volts only for very small systems. Why not 48 volts in vehicles? Because 48-volt alternator chargers are expensive and hard to find. 24-volt and 12-volt chargers are much more common. Also, in vehicles with partial shade, parallel panel wiring works better, and 12-volt systems allow that more easily. This is Michael from Battery Hacker. If this helped you, like the video and subscribe. I will see you in the next one.